Hey Aiden, we hope you are feeling okay and better, maybe. This is the last two examples on 4-6, and this is the last section before we're done with chapter 4. So we're going to go through these two story problems, and then it's going to be hopefully a short video here for you. Carbon 14. We're talking about radioactive decay. So if I'm gonna mark it on my thing. Whoa, Josie. She was just going crazy, I guess. Radioactive decay. So if they ask for a question on radioactive decay, refer back to example 5. Carbon 14, also known as radiocarbon, is a radioactive form of carbon that is found in all living plants and animals. After a plant or animal dies, the radiocarbon disintegrates. Scientists can determine that the age of remains by comparing the amount of radiocarbon with the amount present in living plants and animals. This technique is called carbon dating. So they will take like a person, like of the same build and same size, whatever, and then take a dead person and compare the carbon 14 and figure out how long that thing has been dead, right? Do you know what carbon 14's half-life is?
No. Probably 0.00.
Half-life carbon 14 is 5730 years, which we will find in part A. It says find the half-life of carbon 14 using this formula. Great. Okay, now, I think we had some examples that were like this yesterday, and you were like, I don't know what to do. Well, now you know. We are trying to find half-life, which is time, right? So we're trying to solve for time, and we're trying to figure out half-life. Okay? And so that means that we have to plug in numbers in here for A and P, right? And we just get to pick those. So whatever you want. How much carbon 14 do you want to start with? Doesn't matter. 2, okay? And if we start with 2, after like it has split in half, it will be 1, right? Okay, so that's the way that works. Okay, we could pick anything we want to for those guys, because when we, just as long as they are like in the half ratio, and we're just solving for t, okay? So first do algebra, divide by 2, so he is gone. And then we're going to ln both sides. Yep, so ln of a half and ln of e, that's going to cancel, right? So we have ln of 1/2 equals negative 0.00012116t, and then divide by that blah, blah, and that will give you the carbon 14 half-life. And it should be something close to 5730.
I got 5,700 exactly.
5,700 exactly.
Yes. Well,
Okay.
Oh, 5,700.2235.
Okay, let's go 5,700. Okay, it should be 5,730, but rounding and all the things, right? Okay, so that is part A. That is 5,730 years. Charcoal from an ancient fire pit on Java contained 1/4 of a living sample of the same size. Estimate the age of the charcoal. Okay, so here's the deal. If we start with, like, let's say 1, right, and it splits in half, now it's a half. If it splits in half again, now it is a fourth. So when they say 1/4 of it exists now, how many times is it split in half? Twice. So how long has that thing been dead? 5,700 times 2. And that's all. Whatever that is. 114 with 1, 2, 3, 4 zeros.
2 zeros.
2 zeros.
Oh yeah, I'm not squaring it. 2 zeros. So 11,400 years. Approximately. And that's how they figure that out. They measure what it was, what it is now, and then they compare that to what it probably should be and figure out how long it's been dead. Yay! Okay, example 6. Newton's law of cooling. Oh, I was just telling Layla about this morning. We were talking about like how things put in a different environment will absorb the temperature around it, so it will become the ambient temperature. We did a lot of studies on this. I took a college class in my grad program that was called Math in the Real World, and it was really interesting. We studied vaccines versus like epidemic outbreaks or whatever of like measles and stuff, which is kind of interesting because right now there's measles outbreaks. We also studied like how they know how long a body's been dead. So like when you go to a crime scene and they're like, oh, we're estimating that, you know, this person died somewhere between 9 and 9:30 p.m. the night before. And we're like, how do you know that? it's because of the temperature of the body. And like, they can also compare that to like when the person ate and how much digestive matter is in their like colon and stuff or whatever, like how long their food had been digesting or whatever. They can compare it to that. But this one is like how cool the body is, right? So it takes a certain number of hours to reach the ambient temperature. They take the temperature of the room. They figure out how long it should have taken. Now, other variables into consideration, like if that body is in a pool of water, obviously it's going to cool faster than if it's just in regular room air, right? Or if there's a fan blowing above them, it's going to cool faster. So they have to take all of those things into consideration, and there's like tables upon tables upon tables of like variables that they consider. Anyway, Newton's law of cooling says that the rate at which a body cools is proportional to the difference in temperature between the body and the environment around it. So temperature of the body is like the first variable. The environment around it, that's like the ambient temperature. And the temperature of the body, that's F of T. So this is the body temp. Units after being introduced to an environment having a constant temperature of T. This is the ambient temperature. So this is like the room temperature. Okay. C and K are constants. And there we go. All right. So a pot of coffee with a temperature of 100 is set down in a room with a temperature of 20. The coffee cools to 60 degrees Celsius after 1 hour. Write an equation to model the data. All right, so what do we put in for the body temp? Because we're not talking about bodies anymore.
100.
Yeah, that's what it starts at. So 100 goes in there. I'm gonna put A down here. Okay. The ambient temperature is 20. Okay. Plus, it says the coffee cools to 60 degrees after 1 hour. So what is C?
60 or is it?
I think C is 60. Let's see, what is it called? The temperature F of the body at time T in appropriate units after being introduced to an is T naught. Oh, after being introduced. Got it. C, we got these switched around. C is like your P, right? And the principal amount is 100. So this is how this works. 100 goes here. The after amount is 60. 60 goes in this spot, right? Like that's where A and P would go. Okay, it's just that we have this extra 20 in here, okay? E, negative K, and T is 1 hour. Okay, and there are my units in hours. Time and appropriate units, so it doesn't say units. Does that make sense? Like if we had this in terms of A equals PE to the RT power, the only thing that we have extra in this equation is the ambient temperature because that's taken into consideration. So P is the principal, that's 100. After amount is 60. So that's kind of how that works out. Okay, so we've got this thing going on. Now what? We've got to solve for K, which is the constant.
So we can take 60 divided by 20.
Not yet. Nope. We gotta subtract 20. Right? So 40 equals 100 e to the negative k times 1. Divide by 100.
Then ln.
Yep. So divided by 100, that's 0.4 equals e to the, and k times 100 is negative k, right? Okay. So then I just ln. What? We're just doing the math.
I know. Where did you get negative?
What? Where did I get this? So k is is from the formula.
Yeah,
Negative kt. Oh, I'm sorry. Negative kt. Oh, yeah, that's a k. Yeah, he looks weird. That's negative. Yeah, it looks like 1c. This is a k. Okay, there you go. Negative k times 1. All right. So if we divide by 100, we get 0.4, and then we ln both sides, right?
Yeah.
And that gets rid of that, and that's negative k equals whatever that number is. Then we're going to divide by negative 1. So k equals
0.916.
0.916.
They're gonna be negative, that is.
Okay, but let's check the answer A. Write an equation to model the data. So now all we need to do to write the equation is like f of t equals t naught plus c e to the negative 0.916 t. We just plug that in and leave all the other variables there, right? After we've solved for k, we plug them in. There's that. Okay. That's what he will look like. All right, find the temperature after half an hour.
So it's just gonna be
So what are we finding in the formula?
T. No, the final thing.
The f of t. So this is what we don't know. We don't know f of t. Okay. T naught is the ambient temperature. That is
20.
20 plus c is what we're starting with. So 100 e to the negative 0.916. What do we plug in for time?
30? I don't know.
The initial time that we plugged in was 1 because this was 1 hour.
So 0.5?
So our formula is in terms of hours, so we plug in 0.5 for a half an hour, right? And then we should just be able to like type that whole thing in.
I got 83.25.
83.25 degrees, does that seem appropriate? After 1 hour, it's 60 degrees. After a half hour, it's 83.25 degrees, right? Okay, yes ma'am.
Could you record fourth period for me today and send it to me?
Mhm.
Because I think Kate's coming to the school to help me with my speech.
Sure, yep,
I'll probably be gone the whole time.
okay, sounds good. Okay, that was B. B was that guy. How long, okay, so hold on, how long, that means we're solving for time will it take for it to reach 50? So where does 50 go in?
Final.
The final. Final is 50. Ambient temperature was 20. 100 goes here. E to the negative 0.916, but we're solving for T. So this is going to be similar to part A when we solved for K. All right, but we got to do all the other things. So we're going to subtract the 20 first. So this is 30, and then we're going to divide by 100. I got a mess. 30 divided by 100 is 0.3. So now we're at 0.3 equals e to the negative 0.916 t. That was a lot. ln both sides. That cancels out, and then I'm going to divide by negative 0.916. And you get a time of 1.31 hours. That should sound about right. Now, 100 degrees Celsius is boiling, true? 50 degrees Celsius is like still decently hot, right? Isn't it? I don't know, how many degrees Fahrenheit is 50 degrees Celsius? That's still like 100 degrees. What?
106.
106, something like that, right? 50 degrees, 106, so that's still warm. Like, that's not gonna burn your tongue, though. 50 degrees is not gonna burn your
100
tongue.
degrees Celsius is 212 degrees Fahrenheit, but 50, just take 212 divided by 2.
Kind of, because it's not,
It's
like,
not exact,
they're not,
it's a rough estimate.
right. Because they're not both centered at 0.
Why'd you give us
So
so many
one's 32
homework
and one's
problems,
0.
It's a rough estimate. but it
Yeah,
should be
yeah,
somewhat close.
it should be somewhere close to 106 degrees, so. Something like that. It's not gonna burn your tongue at 50 degrees, it will at 100. So, there you go. Okay, all right, and homework from there. There you go.
Stop
Yes.
recording. And then
Oh, okay, goodbye, Aiden.